In this problem, we're moving on to problem 11 in the practice test. We are given a lossless transmission line with per unit length capacitance is 2 pi epsilon naught over ln of b over a, that's right there, and per unit length inductance on this line is equal to mu naught over 2 pi times ln of b over a. That's written a little bit ambiguously in the problem statement, so if you looked at this problem and thought that ln of b over a was on the bottom of the fraction, it makes sense that you would read it that way, but that's not the right inductance value. It should be on the top. So in part A, we are asked to find the characteristic impedance on the line, which we normally write as Z0 or sometimes ZC. Since we have a lossless line here, the characteristic impedance is equal to square root of L over C. So all we have to do now is multiply that out. So let's see, we got mu naught ln of b over a over 2 pi times 2 pi epsilon naught. Oh, sorry, that's if I multiply by c, I need to divide by c. So if I divide by c, ln of b over a goes on the top, and then I have 2 pi epsilon naught on the bottom. Simplifying that out, I have Z0 is equal to square root of mu naught over epsilon naught times square root of ln squared of b over a over 2 pi squared. So if you remember, square root of mu naught over epsilon naught is eta naught, the intrinsic impedance of free space. So this whole thing works out to be eta naught over 2 pi ln of b over a. My ln is kind of crazy looking, but you get the idea. So that's our characteristic impedance on the line. Next, we're asked for the propagation constant. For a general line, the propagation constant is equal to gamma, but for a lossless line, the propagation constant is beta, because alpha is equal to 0. So that propagation constant is going to be beta, which is equal to omega times the square root of L times C, which again we just have to multiply out. So we have omega times the square root of mu naught ln of b over a divided by 2 pi times 2 pi epsilon naught divided by ln of b over a. Now in this one, everything except for mu naught and epsilon naught is going to cancel out. So beta is going to be equal to omega times the square root of mu naught times epsilon naught. And in general, in a transmission line, you will get that because of the fact that we're having TEM propagation. The propagation constant is going to be a function only of the material parameters, not of the geometry. For the last part of this problem, part C, we are asked to find the ratio of B over A to make the characteristic impedance equal 50 ohms. So let's go back up to the solution that we had for that. Z0 is equal to the intrinsic impedance of free space divided by 2 pi times ln of B over A. If we set that equal to 50 ohms, now we just have to do a little bit of math. So multiplying through by 2 pi and dividing by eta naught, I have ln of b over a is equal to 100 pi ohms divided by eta naught. Now eta naught, if you remember, is 377 ohms. So we have this on the top, we're going to have something around 314 ohms. On the bottom, we're going to have 377. So ln of B over A is some positive number that is less than 1. Meaning that if we then take the exponent of both sides, then we have B over A is equal to e to the 100 pi over 377. And that is going to be some fractional power of e. So it will be greater than 1, but less than e itself. All right, there we go.